Okay. Is this working? All right. Let's pick the next thing to do. And also, I had some ideas of things I'd like to add. A waveform viewer would rock. It would be nice to be able to put text comments, like little annotations or something. I will have to think about how to do that. So if I take a look at my sprites here, I've only got 5 plus 4 is 9, plus 16 is 25. I mean, even if I were to use all of these for letters of the alphabet, I still wouldn't have enough space, and then I wouldn't have any space for other stuff. So there is a hack that you can do that I have seen done in an NES Mahjong game. What you do is, all right, let's draw a letter. So the letters in Pico 8 are 1, 2, 3 by 1, 2, 3, 4, 5, with a single line in between them. So what you do is, okay, hold on, let me draw myself the 1, 2, 3, whoops, by 1, 2, 3, 4, 5. So this is the size of a letter. Now you may be wondering, why is it that I'm insisting on using tiles for the letters? And once again, it's all because of I want to be able to save and load from the map section of the cartridge. Actually, there's something I need to check in the memory. The cartridge. Oh, actually, sorry, I just realized I don't think I have the, yeah, okay. One sec. I'm reading the docs here. Yeah, here we go. So I just want to check the memory map. Okay. Card ROM. Same layout as base RAM until 4300. While using the editor, the data being modified is in cart ROM, but API functions only operate on base RAM. Pico automatically copies cart ROM to base RAM in 3 cases: when a cartridge is loaded, when a cartridge is run, when exiting any of the editor modes. Now, 0x40, 4300. What is that? 4300. Well, that also doesn't help, but it's certainly not 32K. So, but we've got 32K of cart ROM. Yeah, so map 2 is up here, which is a little weird, but that's okay. We got GFX flags that I'm not using. Oh, that's strange. How can they fit the song in just 256? Oh, this is the pattern table. Okay, the sound effects is pretty big, actually. And then user data. User data has no particular meaning and can be used for anything. Interesting. Persistent cart data is mapped to blah, but only if cart data has been called. Color format is 2 pixels per byte. The graphics map and stream memory areas can be reassigned by setting values to the following addresses. I don't understand. The cartridge is 32 kilobytes. How come it ends at 4300? Okay, let's do a little experiment. Oh, actually, I was in the middle of explaining this trick that I saw. It's a really neat trick. So, what you do? Oh, actually, I just realized something. I could fit 2 letters in one 8x8 tile. In fact, I can fit 4 using this trick, maybe more. What you do is you draw your first letter, and then you draw your second letter right on top of it with the rule that like one color will belong just to one letter. The other color, say this one, will belong just to the other letter. Let's take some letters with fewer squares so you can see. So let's say we have an L and like an F or something. Well, maybe an L and a D or an O. I don't know. I'm trying to think of a good example. Okay, let's do an L and a letter R. So now the letter R looks like this, I think. And what you do is you take these 2 letters, you superimpose them wherever the color, or wherever the R is by itself, you give it its own color, like this. And wherever the colors overlap, you give a special third color, maybe like, I don't know, this one or something. Like that. And then what you do is with good use of palette switching, you can pick the right letter out of this. And so with 2 letters, you need 2 bits. For 3 letters, you need 3 bits, and so on. So that means we could actually fit up to 4 letters in one space. And with fancy palette switching, we could pick any letter that we want. Well, this is all well and good, but it doesn't really help us save any strings that the user writes. So we can also save stuff inside Oh yeah, I need to figure out what this, so we can save stuff in this persistent cart data, whatever that is. Opens a permanent data storage slot, indexed by ID, that can be used to store and retrieve up to 256 bytes worth of data using dset and dget. ID is a string up to 64 characters long and should be unusual enough that other cartridges do not accidentally use the same ID. Legal characters are blah. It returns true if data was loaded, otherwise cart data can be called once per cartridge execution, so only a single data slot can be used. Once cart data ID has been set, the area of memory is mapped to permanent storage and can be accessed directly or via dget. There is no need to flush written data. It is automatically saved to permanent storage even if modified by directly poking it. Okay. What I don't understand is same as memcopy, but copies from cart ROM. If file name specified the data from a separate cartridge, in this case the cartridge must be local. BBS cards cannot be read this way. Code section. Oh, code section. Duh. It's protected and cannot be written to. Written in one. If file name is specified, the data is written directly to that cartridge. On disk. Okay. So up to 4300, we have this now. Sound effects take up a lot of space. I don't know how they're formatted. Maybe we can squeeze out some space in here for strings. Maybe we can sacrifice some of the map space for strings. Let me think about that for a second. Yeah, there's no need to do this crazy business if we can just store like the string, you know what I mean? So I'm using pretty much all the space I can get for the sprite sheet because of this thing. Well, all right, let's stop and think about this for a second, because if I have fewer than 256 nets, I could just put like a net ID on every tile. And actually, okay, wait. There are some opportunities here because I don't need these. I don't need my duplicate values for the different states. All I need are like one state from each. So I need, oh, actually for these I do need both because of the way I did it. And I'm planning to keep it that way too. So I only need one set of gates. I only need one set of these wire pairs, or one set of these wires. I technically can use up these spaces right here. Although it would be nice to save the state implicitly like that, you know what I mean? Because then when you save it, it saves in whatever state you left it. But it would be nice to have... Alright, what if... I mean, I wasn't originally going to do this. The whole point of going down this road of drawing a bunch of stuff on the map, in the sprite sheet and all that, was to make it easy to save and load, or as easy as possible. It also means that it's possible for you to draw circuits using the map editor and do that. But what if we just straight up serialized Okay, here's something. I think that I just need to serialize my global tables of elements. I don't think I need to serialize the grid because every element keeps its coordinates. Honestly, that may be easier. Because then I could put labels on nets. I could put labels on any of the components. I do still think I'll keep this technique here of having the different sprites for the different states. It has led to a fairly streamlined simulation loop. Like, don't worry, a lot of my code is just outright spaghetti, but the simulation code is actually pretty good. And this technique is what made it possible. So I think I'll keep that. I think I will also keep... Excuse me. I woke up at 6 today, which is pretty good actually, but now I'm a little tired. Anyway, what was I saying? Yeah, I think I'll just serialize it into a big long string and just save the friggin' string. Let's do an experiment with that. So type to num equals, oops. So gate is 0. No, let's do net is 0, gate is 1. Reg is 2, junction is 3. Okay, let's just go for the format. Let's try and explain the format. We need a header to say what kind it is, so header, let's make this 1 byte. Technically a net can have an unbounded amount of coordinates in it. I mean, I really want to be space efficient here. Well, do I need to be that space efficient? Yeah, I do, because all of my numbers are 16 bit. Well, no, because, yeah, all of my numbers are 16 bits, like my coordinates. You see, when you serialize, when you like basically write it to the grid and then save the whole grid, you don't have to save the coordinates, right? But every coordinate is 16 bytes. So or not 16 bytes, 16 bits. So technically, if all I had was one net that covered the whole grid, which I'm not sure why anyone would bother to draw that, but even if they did, you would expect it to fit, right? That's kind of like the worst case scenario, I think, is a net that covers the whole grid, because I have to save all the coordinates. But we do have one trick up our sleeve, which is that nets are expected to be connected at all times, which means that you could probably just save all the DFS traversals of a net. And then that way you would only have to save the first coordinate and then the diff to all the other ones. And then for us, the diff could actually be a 2-bit number that says what direction you went. So the header needs to have the type. What else can we put in the header? Can we fit the coordinate in the header? What's my span of coordinates? Yeah, actually, my coordinates are only, I think, 128 by 64, right? Or technically. So, yeah, I don't need 16 bits per coordinate. So let's start by data types first, and then I'll just call it element format down here. So data types. A coord is 128. A coord indicates 1 square of a 64 by 128 grid. So we only need 6 plus 7 equals 13 bits. So that means that our header can be the type and the coordinate, 2 bytes, type and coord. What I'm calling a DFS chain. Actually, let me format it. Let me organize things like this. DFS chain. We can save space when serializing nets by using the fact they are connected. Or DFS chain, I'll call it a net traversal. A net path, let's call it a net path. They are connected. A net will be described as several paths Wait, I just thought of something though, because like if you have a sort of a corner case, let me draw it out here. If you have a corner case like this is something that, wait. Well, yeah, I mean, let me just draw it like this there. I think you get the idea, but if you do something like this, like the DFS is really going to struggle on this. This is kind of the case where it's kind of like when you get like the worst case when you do like you're doing binary trees, but the worst case is a linked list, you know, it's kind of like that. So here, you know, we'll definitely get, I mean, well, even worse is if we happen to start our DFS traversal in the center here. So we'll get like one path that might go all the way to the left end, one path that might go all the way to the right end. But then we're going to need paths for all these other guys. And then we're stuck to, if we're not careful, we'd be stuck to having to put a bunch of 13-bit coordinates again. Now, we know that every node has a maximum of 4 children. So how do you serialize an unbalanced tree? Because so if I were to take any arbitrary net and draw it as a tree, it would kind of look like this. We have a node. It can have up to 4 children. Each of these can have up to 4 children. Well, you get the idea, you know. Right? That's strange. I don't think that should have connected. Wait, hold on, is this a bug? Oh, duh. It's because it looped around through here. Right. So, right. No wonder. Okay, it's not a bug. It's, that's how it's supposed to work. Anyway. And, you know, maybe this node has a few children on it. And then, you know, and so the DFS traversal would create for you sort of a tree like this, right? We want to serialize this tree using the fact that, except for the root node, the encoding of where, let me say it differently. If I were to take 2 different nodes on this tree, the difference between them is actually just a 2-bit. It can be encoded as a 2-bit value because we know that they're neighbors in the grid, which means that they're either up, down, left, or right of each other. Yeah, that means that if we can figure out a nice way to serialize a tree, then the only thing we need to do is for the root node, we give it a 13-bit coordinate because there's no choice, we have to do that. But then for every other node, like say this one right here, we only have to give it as a 2-bit value. And if we're careful, we can pack them all in. Now, I'm reminded of, okay, it's time to open up MS Paint. I mean, or actually even better, we can use XCaliDraw. So, I remember Sean Parent had a really interesting talk once that when it comes to trees, and in fact, not necessarily just trees, but let's start with a tree. Let's start with a binary tree just to keep things simple. Oh my goodness. I think I'm really zoomed in. Man, what do I have in here? Just random stuff. Anyway, so let's say you have a tree, maybe like this. Let's say it's an unbalanced tree, so you have some stuff like this, like that. There is a way that you can traverse this, which is what you do is you imagine that, or here, let me draw. Okay, hold on. I need more space to draw. What if I just maximize this? Okay, let me first turn that off and then do this. Yeah, I think that works. So what you can do is draw this same tree by following a. So he described a toy that his kid had, which started out as just a loop of string, and you had all these beads. Oh my goodness, that's the worst bead anyone's ever drawn in the history of drawing beads. Okay, that's a little bit better. And what you would do is you could grab a little bit of the string here like that and push it through a bead. So what you would then have is something like this, right? And you can draw a tree. Oh yeah, okay, that's right. You can't draw cyclic graphs this way. You can only draw trees, but that's okay because that's what we have. What I can do now is I can draw a traversal of this tree that goes like this. Like that. And if I were to draw this as like beads and strings, I would, every node would be a bead, which I'm just going to draw beads like this, thank you very much. So our string would come in here like that. And then this node is another bead, that's a bead. So we'll put a bead here. That talk was really good. It was just a really amazing way to look at things. I forget what it was called though. It was one of the, I think it was one of his CPP-Con talks. Just disclaimer, I don't know anything about Sean Parent. Except that he works for Adobe. So this would come like this, I think. And go here like that. We technically have a bead here. So it would go like this. I think you get the point, but I'll finish drawing a little bit more of it here. Well, yeah, let's just finish drawing it. I only have one more node anyway. Wait, what beat is what? That one, that one, that one, that one. Okay, we need another one here. I mean, I'm not winning any awards here for nice drawings. And then we finally need one last bead here. Something like this. Oh, wait a second. Did I do this wrong? This needs to have two children. Oh yeah. Oh, all the leaves are nodes. Or right. Right. So let me just. Right. I forgot about that. All the leaves are nodes. So what that means I need. Anyway. Yeah. So tuck 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 like this. And, oh yeah, this is wrong. Ugh. Actually, okay, there is a point to redoing this here, because the way I did it was wrong. And actually, when I do it correctly, it will be more illuminating. So let me first draw all the nodes in roughly the same positions that they are in the other diagram. And then I'll draw the string. So then we have this. Then we've got one here. So this one has two children. This one only has one child. This one has two children. This one has two children. And so the rule is the string coming down on the left here goes from parent to child, and the string coming up on the right, so then we have a loop like this, a string coming up on the right, I think goes to siblings or back to the parent, like this. Oh, I guess I forgot this one too. There, I did it. I got a little messy over here, but I think you get the idea. Now, the whole reason for doing this is that this, I think, is a way to, not just to traverse the tree, but to serialize it. Because, I gotta think about this here. We started the root, right? The root is just gonna be a 13-bit number. So this is just this is root 13-bit number. No avoiding that. Now, this link here, this points to a child, and there will be some, like, let's say that this child is to the left of it or something, right, to the left. So that means that here we can infer the coordinate, right? So this here is has an inferred coordinate. Well, basically everything except the root has an inferred coordinate, you know, so all of them, etc. Right? This is another case of child left, and then this is a case of, well, I guess we don't need this. This is a case of sibling. Oh, well, I said this was to the left, so let's just pretend it's to the left anyway, right? So what I'll do is I will mark in blue the things I actually need. I didn't mean to make that black, by the way. Although the beads do look better when they're a different color. So maybe I will do that. So what I'll do is I'll mark in blue everything that actually needs to be saved in our serialization. And if we're careful, this should actually take less space than my original idea, which was to just straight up like save the whole map. Remember that every tile of the map is a byte. I'm not also going to get rid of these here, like that. So let's suppose that this node, I'm just going to make stuff up here, was down from, so I'm using a slightly different blue here, but whatever. And then this is a sibling. And let's suppose that it was to the up, or whatever. And so I think you see what's happening here. We have 3 cases for the first tag, which is whether this is a child. Oh, actually, we can even make this 2 cases. We can still call this. Oh no, we can't, can we? I think we do have 3 cases, right? And you know what? Maybe these sentinel ones really are a good idea. No, maybe not. Okay, so we have 3 cases for the first part of the link, and we have 4 cases for the other part. I mean, technically, right? It's not all 4 because we don't allow nets to fold back in on themselves, so we could even squeeze this down. But that is insane. Is it though? I mean, we're down to 7 bits, which is kind of a pain in the ass to serialize if we want to pack them all in. But, you know, anything, if we can just pad it up to 8 bits. I mean, again, anything a byte or less means that we are doing better than the original layout. Wait, is that true? Because I need a bunch of, I do have this 113-bit coordinate. Man, this is tougher than I thought. I thought I'd be able to just like figure this out, but by the way, so when I'm drawing this diagram here, this left, down, and up, I'm just making them up, right? These are just things that would be tagged on the tree in the serialization. I'm drawing it here as like an abstract data structure, and what I was going to do was after I made up values for all of these, I would have deserialized it back into a grid representation. I'm just checking to see if anyone left any messages. Okay, so like for example, you know, I start with the root, right? I start with the root, and then I check its next pointer. Its next pointer says it's a child. So the child is talking about this graph here on the left, but then the direction talks about where the connection is in the grid, so we put one to the left. Now we have a child down, like this, right? Now here's the thing. If you see sibling, this means go back to their common parent and go that direction, so that means go up, right? And then this one here has a child, you know, maybe this is to the left, and maybe this is to the left, and so on and so on, right? So that's how you would deserialize this back into a net, right? So what you would do is, as you're going, you would write down your inferred coordinate for each of these, and then every time you follow a link, calculate the coordinate based on the inferred coordinate of the parent. It's kind of amusing that Sean Parent's name is Sean Parent. Anyway, so I feel like I can do better than this, though. I just have that feeling. I can't justify it, but oh, what time is it? 8 o'clock. I need to go in an hour and a half. Anyway, what I really don't like is that there's 3 cases for this first part of it. It feels like I should be able to make that into 2 cases. I almost just want to pull up that talk by Sean Parent and listen to it for a bit. All right, let me do that. I'm just going to... it's bad enough that you saw my recent Google searches, but I think I don't really need to show you my YouTube recommendations. Let me pull up that talk by Sean Parent, see if I can find it. Here it is. Yeah, this is it. Okay, and let me turn on the, I guess the sound is on. Okay. Yeah, this was a really cool talk.
I've got plenty of time for questions. People have any? A question over here. You might want to come up to the mic if you can.
Okay, hold on. I'm looking for the beads. Show me the beads. Is this it? Ah, yes. Okay, here we are. Beads and shoelaces. He's talking about the beads. I guess it's diagrams, and not that they're that nice looking, honestly, but they're still better than mine. So he is encoding. He is encoding each of these arrows as pointers. I think I understand. Wait, do I understand?
A post-order depth-first traversal. Move things. Okay. There is nothing that you can build with this physical model except for hierarchies. It also has some of these properties. In that, right, it's a little bit more complicated direction. Okay. So we have the knot at the top. That's the piece that we hold on to. That's our forest. Okay. We can add a directionality to the string as far as
Sorry, that's a little too fast to hear him clearly.
Moves around. Okay. Each position here represents a position where we could draw that out and insert another node. Right? We can't reparent things, but we can put leaf nodes anywhere. Okay? Just like on our original string, if we were just putting beads on to form a list, I can't move things further up without splicing. Okay? But I can keep that ordering. In a similar way, I can always add leaf nodes to my tree, but I can't reparent things. Okay? Every position within this list uniquely identifies a location within the tree without keeping a stack of information. I can have an iterator that points to a node, and I can just remember it and pick up from there and keep going in a traversal. Right? If I give you this definition that says we have a leading and trailing edge on our nodes, okay, then if I mark off the leading edge where I come in on the top, that is a pre-order depth-first traversal. And coming up from the bottom...
Okay, hold on. Pre-order depth-first traversal. Yes, okay. Pre-order, I don't actually remember what pre-order means, but depth first for sure, right? Because if you just follow this, it's definitely depth first. Definitely.
Is a post-order depth first traversal.
Oh, post-order depth first. Okay, so if you follow the trailing edge, I guess if you go backwards through here.
Okay. If I want to know what it means to erase elements from some point in my model to some other point in my model, okay, what I do is I grab those 2 locations on the string, and I pick the whole thing up, and the beads that fall off are the ones that get erased. Okay? So above my fingers, going towards the knot, nothing can come off. Below my fingers, things might get stuck if I grabbed along the same edge, I might end up with a list of parents that I didn't fully select. The string has to go through twice for it to fall off between my two fingers. Okay. This means that if I take this structure and I flatten it out and I encode it within a UI, it means that I know what it means if I click here and shift-click there and hit the delete button. Okay. And the algorithm in the code for this actually works out to be see what beads fall off. Right? It's quite a beautiful little thing. So there's a forest data structure that's in ASL. That's been in ASL for years, Adobe Source Library. You kind of know what it is. It's decaying a bit, the source libraries are, but I keep this up to date on GitHub, so you can find the ASL repository on GitHub, and this will build. And this is what it looks like to insert things. And in my opinion, this is a really beautiful data structure. It's not a particularly efficient data structure. It's a node-based data structure, but that's what you would probably create anyways. But it has this wonderful safety attribute that I can't create a non-hierarchy. Okay? So it has these wonderful attributes that I can remember positions into it and deal with that. That when I iterate a range, I can see what it is exactly that I'm iterating. Okay? I'm not calling each node and saying, you call your children somehow. Okay? And I know if I want to do a pre-order or post-order, that becomes immediately apparent within the code.
Okay, hold on. Is he going to explain that example?
A little side story here.
Oh yeah, that's a story that he was telling. I'll let you watch the video to hear that story, but it's kind of amusing. It's also kind of upsetting, honestly. You'll see what I mean. It's a good story. You should listen to it. But anyway, let me walk through this example in my head. So first we start with a forest, then we insert A. We insert at end of F. So I guess end. So these must be like double links, not just like a single pointer from forest to A. I think there's a forest to A and then a back pointer from A back to forest. I think all these links have 2 pointers. So you do end of F, which at the start of everything is just F, and then you insert A. Okay, so we insert A. Then end of F is now pointing to A, and then we insert E. So inserting creates a sibling? Oh, no. If we insert at the end of F is still F? So this is some kind of iterator, end of F. And end of F must be equal to F. And trailing of is some kind of iterator? I don't know. I'm not really sure I understand this. But the question I have is, suppose you were traversing this. How do you know if the edge you're following points to a child or to a parent or to a sibling? And I think the answer is you don't. Like this trailing edge, again, I don't understand what this trailing of means here, but this trailing edge coming out of B, here it points to a sibling, but here it points to a parent. And I think the only way you would know that is if you happens to be keeping some sort of state as you were traversing it, and you would be like, oh, hey, like you keep a stack of all the parents that you've traversed, which is what I have to do. You'd be like, oh, hey, this points back to A. Except for me, these aren't pointers. I'm not having them point to different spots in the tree. I'm not having them point to data structures in memory. I'm basically just labeling them as whether they go to a child, sibling, or parent. So actually, I guess there really is no way of knowing whether a link points to a sibling or a parent. Well, okay, one thing we know for sure, is that the very first link we follow is a child, always, right? So now the next link we follow could be a child, or it could be a sibling, or it could be a parent. Yeah, okay, there really is no choice, I think. I think we do just need the 2 bits there. So two bits plus 4 bits. Oh, for some reason I thought, oh, there's 3 possibilities, but only 2 bits. So 2 bits for the type, and 4 bits for the direction in the grid. Technically we can squeeze this, but there's no point because we wouldn't save any bits if we did that. Wait, is that true? We have 2 bits for this. Oh wait, no, 4 possibilities, 2 bits. I don't know what I'm thinking there. This is just a 4-bit number. That's great, actually. That's really good. So the first 2 bits is the relationship, and the second 2 bits is... Oh, actually, that is great, because now we can put 0 for the relationship type to mark that we're done. So I don't even need to encode the length of the tree. So let's do an example. I think it'll be really useful to do an example. Let me draw something just a little more, ordinary. Let me think about this. So, I don't know, let's say I was drawing a clock generator, and that it was feeding into a flip-flop. Something like that. Wait, hold on. There should be a frame here, I think, where they're both on or both off. Yeah, both on, which I think is actually okay, come to think of it. I think that helps with stability. Anyway. So let's think about this net here, this one here. So it comes around like this and like that. This is going to be, oh shoot, I just realized I wasn't sharing the, okay, let's go back to this and then that. So this is what I just drew there. So let's take this net here that comes out of the gate, goes around like this. We will have to serialize, by the way, the gates that we connect to. I will think about that next, but let's first start by talking about this net here. And, just for the sake of example, let's have this connect to, I don't know, a latch or something, right? Whatever. So let's think about this net right here. So I actually would be able to see it in my net dump, probably. Oh, I don't think I have the net dump turned on. Man, I've got a lot of debug stuff in here. Well, let me just draw this out here. And let's just take arbitrarily the point that I have highlighted there in blue as the root. So let me just get a grid to work with. It's hard to find a good grid for some reason. Oh, that's nice, actually. So I think you can copy and paste images into Excali draw, hopefully. Now, what we have is, so I'm just going to pick this arbitrarily. We have that, 2, 3, 4, 5, comes down like this, 2, 3, then 1, 2, and 1. I guess this doesn't have to be accurate, but you know, comes down like that. It's also here, and then it goes off to the side like this. Whatever, I'll just draw a few of these. Whatever, that's good enough. And I have said arbitrarily, actually this may lead to a less interesting example, but I've said arbitrarily that my root is this one. And so let's draw a quick sketch of the tree. I'm not going to draw like every single node. But that means that the tree kind of looks like this. We've got this, which has 3 children. One of them is just a single node. One of them is like a long chain of stuff. And the other one is like a long chain of stuff. So how does this get serialized? Well, first we have the root. So now I'm just going to start trying to type it out here. Maybe I'll do that here. So the root is going to be at 12, 6. And then we have then we have a child pointer, which is down. I think I have it down on this keyboard layout. Oh, but it doesn't have the Unicode character for it in Excali draw. Okay, so I'll just go C and then down. And then we have a sibling, which is up. And then we have, so then we have child left, right? Child left, child left, child left, child left, child left, and a bunch of child lefts. But then we have to go up like 10 parents. And a parent doesn't give us any information about a new node, so So it's like, okay, maybe one thing we can do is for parents, the 2 bits. Okay. We can have a rule. Okay, let's think about this here. And that would be described as the traversal of a tree. Every element of the traversal has format bit 5, parent, or bit 5. If 1, this is a parent or sentinel, or well, sentinel, or just like end marker. If 0, this is a child or sibling. Oh, no, we have 4 bits, so bit 3 If 1 is a parent or end marker. If 0, this is a child or sibling. If bit 3 is 1, we read bits 2 down to 0 as the number of parents to unwind. I can't think of a better term right now. If this number is 0, then it's an end marker. Well, do we need that though? Because if we're unwinding parents, like eventually we're going to unwind back to the root node. This is a parent link. The number of parents to unwind -1. For example, 0B100 means 0 means go up 1 parent. Means up 1 parent. 0B1, I don't know, 101 means up 6 parents. If you pass the original root, then the traversal ends. If bit 3 is 0, we read bit 2. If bit 2 is 1, this is a child, else a sibling. Then bits 1 down to 0 indicate the direction in the grid between the 2 nodes. I think this works. Save space when serialized and when using about there connected to the net will be described as the traversal of a tree. The first part of the traversal, we don't need to pack it into 13 bits here, there's kind of no point. The first part of the traversal is the x and y cohorts of the root, 1 byte each. Then every element of the traversal has format. So right, I forgot I did that. So actually we are using the fact that we can pack it in. Yeah, fascinating. Under 2 bytes type net. This is in type enum between net gate reg junction. So that's 2 bits. right now needs 2 bits, but we will reserve. How many bits can we get? 13, 16 minus 13. Oh, we only have 3 bits left. To have only 8 types is a little limiting. It's a little limiting. One thing we can do is a coordinate relative to the last grid element that we serialized. And then if we could fit the header in 1 byte, then we're back to, because right now if it's 2 bytes, then if you just fill every square with a gate, not sure why you would do that, but if you fill every square with a gate, excuse me, you wouldn't be able to save it in the map area. What's the time? 8:30. Still have an hour. The header really should be, okay, so we need a move to command. This is 2 bytes for sure, because we need a special, yeah, we need to fit like components like gates, junctions. Oh, junctions though, junctions need to say whether they're abutting or flyover. Okay. If in the diff so a move to command takes 2 bytes, right? So long as, how do I explain this? Like, let's say I was serializing, I don't know. Let's say I was serializing like this, and then that, and then maybe over here this, right? So long as I can, or even this, so long as, so move to command takes 2 bytes. Now, right now my rule is I have to be able to save individual gates as a single byte. Individual gates, junctions, components, whatever, as a single byte, unless they need extra data. So a net is an example of something that needs extra data. But we're saving space on the net right now with our tree traversal. I think we're saving space. We might not be, but it's pretty comparable. Wait, is it comparable? One nice thing about this beads and strings is that it lets us reason really easily about how much space it's going to take. Now, I save a little bit of space by allowing the parent type to indicate a bunch of parents to jump all at once. But let's suppose I didn't do that. Let's say I just had a parent, and parent means just go up to the next parent. Then I have 2 links per node, right? 2 links per node. Yeah. So that means if I have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, this might be a bad example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9. So if I have 9 elements in my net, then in theory, that means I need 18 of my links. But each of my links is 4 bits. So I'm back to actually 9 bytes, right? So I'm exactly even on space, and actually I save a little bit with this trick of having the parents be allowed to go up more than 1. So I'm actually saving a very slight amount of space by doing this, which is a little actually not great because all the space I save is what lets me save string labels for things. So yeah, we'll deal with the string labels later though. For now, I'm just worried about even just serializing it in the first place. So yeah, okay, so we're good on space for this. Now, the thing about the move to command is, so long as the space of a move to command is less or equal to the empty space that we're moving over, then we're good, okay? So like, if I have a bunch of back-to-back gates, then it's fine. The move to command is like, you know, diff of 1, diff of 1, diff of 1, put in the gate. Or, no, sorry. I'm really struggling to explain this. It's not as difficult as I'm making it sound. But let's say we had something like this, where we would have a move to whatever coordinate this is. Actually, you can see it on the bottom there. Move to 4, 0. That takes 2 bytes, right? But then every gate would be 1 byte after that, and we are able to do that because the coordinates relative to each other are very small, right? We just move 1 to the right, 1 to the right, 1 to the right. We can encode that very easily within a byte, while still leaving space for the type of the element. Now, if we needed a move to command, it would have to be for a case where we can't fit the distance between 2 gates inside the 1 byte representation. So long as that distance is greater than the space of a move to command, in other words, greater than 2 squares, then we're fine. So if it was blank here in the middle, it would be move 2 to get to here, a 1 byte for the gate, move 2 to get to here, 1 byte for the gate. And that is still either equal to or better than 1 byte per grid square. The absolute, what we really can't do is be worse than 1 byte per grid square. But so far, I actually think we're doing okay. There is one way in which we're worse than 1 byte per grid square, which I'm trying to think about, which is junctions, because junctions belong to 2 nets. But the way I do it is that I actually put the coordinate of the junction in the net's list of coordinates. So, but that's not a big deal. Either I will just not even do that in the first place, or when I go to serialize it, I will check for that case specifically. Oh, but wait a second though. Oh, but that breaks my tree, because the tree depends on it being connected. So maybe I just need to infer junctions. Like just not even save them at all. I just need to infer them. When I'm deserializing, oops, that's my alarm going. 1 sec. when I'm deserializing, I'll just have to keep track of when two nets hit the same grid. So let's write that in as a rule, because now we're back to things working. Serialization note, junctions not serialized. We will infer them from cases where nets overlap. Move to is 2 bytes, and it's just simply the chord. I'm leaving it as 2 bytes because, like, to pack things at odd numbers of bits, I mean, we would save space, but it would just make the code really ugly to have to bit shift stuff around and mask it and all that. So I just don't want to go down that road. And then we just have a element. So the type, I'm going to leave this as 4 bits, so we can at least have up to 16. And then relative x, 2 bits, relative y, 2 bits, and we will take these to be positive. No, wait a second. This doesn't make sense. Just relative x. Maybe 3 bits is good. That gives us 5 bits for the type. And when we serialize the grid, we're just going to read through it in just like scan through it, right? So the worst case scenario here is if your map looked something like you just had like these like a bunch of vertical stripes, because here it would work. Oh, I see. Because here it would work. Oh wait, no. These need to be far enough apart that. Assume these are far enough apart that our move to command. We need a move to command between each one. So this is the worst case scenario. We need to move to command between everything, when we could technically do better by going up just in Y's, but I think that's okay. Because we have enough empty space oh wait, okay. What if every single thing was full? Oh, okay, so long as we allow the relative x to wrap around, then we're still okay. Yeah, we're still okay, so this is fine. So a move to is just straight up the coordinate element. Type is 5 bits. Right now we only have 4 types. Although technically 5 if you count the fact that registers have, oh, more than that actually, because we have register delay 1, 2, and 3. We have junction types flyover and abutting. Oh, we need the negators for the gates. Oh my god, I can't believe I forgot that. Shoot. 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 Oh, and then for the nets, oh man, I'm just... For the nets, we actually need to say what gates they're connected to. Which, I guess we could hack that in by letting the coordinates overlap with the coordinates of the gates. Oh my god. If we let the coordinates overlap with the coordinates of the gates, then we don't need to say what port it is, not what net it is. We can infer it just by knowing the coordinate of the gate. But for the gates, we need the negators. which is already 4 bits right there. For the delays, we need to know the length of the delay, which is 2 bits. For the junction, we need the type, whether it's flyover or abutting. I got to count this out here. So we have 1, 2, plus 16 is 18, 19, 20, 21. So right now we're using 21 different types. We can still fit that in 5 bits. And it leaves us space for 11 more, which is a little bit limiting, honestly. Okay, I have a crazy idea. I mean, now we're really getting into complexity here, but I think it would work. Let's say that our original, actually, let me leave that. Do I still have the grid in my, no, I don't. My snipping tool is still open. Okay, good, at least this is still open. Come on. So what we can do is this. Let's say that originally, okay, we have, you know, we have a gate here. We have, oh, this is annoying. We have a gate here and a gate, I don't know, here and here. Or maybe these are just components. They don't necessarily have to be gates, right? Something like this. Now, right now, the way it is that wires go between them like that. Each of these are nets. So maybe we have something like this. Right. So what we can do, knowing, oh, are we still back to, yeah, so what I was thinking is we know, okay, for a fact that anytime, like this is just our rule when we're deserializing. The rule is, not that we know, we don't know it, we just decided it, but we decided that anytime 2 nets overlap when we're deserializing, we put a junction there. But I realized a while ago, and didn't say anything, that this still doesn't tell you whether it's flyover or abutting. But that's not true, actually. No, it does tell you, because you know that this net is different from that one, so it has to be flyover. Or if you know that this net was different from that one, then it has to be abutting. So you can infer the junctions for free. But there might be cases where what we can do is, there won't be cases of this right now, what we can do is we can make a rule, is that we will add the coordinate where it connected to the gate. Whoops. We will add it in to the net's list of coordinates. That's going to be what we do. And when we're deserializing, we'll have all of these places in the grid where multiple nets ran into the same square, like that. So that means, you know, and let's just draw this as, you know, like that. And let's draw another example where we have something like this, right? So we know when what we can do is we keep track of all of these locations that have, oh, that's cool. Whoa, that's cool. I didn't know CorelDRAW could do that. I don't want it though right now. Anyway, so we'll keep track of all these locations. There was supposed to be one here. And we'll know what these locations are because we're deserializing and we see them. So we keep track of all the locations where multiple nets crossed a square. Now, if we see a situation where more than, like if we look at the square and we look at the nets around it, and if some of them are connected through, then we know these have to be junctions. So we already can detect this without any extra information. So let me mark this in a different color just to say we detect these as junctions. But anything else has to be a gate or a delay or a component, basically, is what I'm getting at, right? This is another case where junctions are just completely different from components, but everything that's left over in blue is a component. Then what it means is we don't need to store the coordinates or the relative position or anything. So long as we follow this list of nets with a list of components, then what we will do is we will say traverse these grid squares, these marked grid squares in order, right, left to right, top to bottom, and the corresponding element from the array of elements at the end of our list is what goes there. And then we can have 1 byte per element if we so choose. We could squeeze it down to 6 bits per element because it is going to cost space for us to add these extra coordinates to these nets for all the gate connections. Let's think about how much extra space this takes. Every node costs, in principle, 8 bits. Every node in principle costs 8 bits. We technically save a bit because of our multiple parent rule, but in general we need a link to it and a parent link out of it. So for every square that has a gate on it, we're costing an extra 4 bytes. It's kind of a problem, isn't it? And I just realized something. We actually can't necessarily tell that it's a junction. Because if you have, I wonder if I have an example in here. There's no example in here, but let me just draw one for you. If we have a situation where, I do this a lot, right, where a gate loops back in on itself like this. Flashing lights warning, by the way. Okay, fine. We have a situation where a gate loops back in on itself like this. Then, how can we tell the difference between this and a junction? And the answer is we can't. Let's back up a bit. Why did I go down this road of serializing everything when I decided ages ago that's not what I was going to do? Oh, because I wanted to save things that aren't immediately visible in the grid, or that don't really fit nicely into the grid, like text labels, for example, or if we hit support waveforms, the user is going to want to set up like a view in their waveform, and you want to save that view. And I was thinking to myself, well, those things don't serialize nicely into the grid. You see, before, when we were serializing, I say serializing, it's more like when we just save the map layout, we know when a wire is connected to a gate because it looks like it is, right? Like, I know I'm using this tile, this sprite here, the curved wire sprite, and it points into the gate, so I know they're connected. And it's like, it's a bunch of spaghetti logic to infer that, sure, but, it works. I mean, what if So first of all, to save extra metadata, like I was hoping that by serializing all of my representations, I could save space to make room for like strings and metadata and stuff. But I was always considering the fact that I might just have to shrink the grid, right? Actually, okay, hold on a second. There is one thing I've been wanting to add for a while, which is like, how like when you're editing something, sometimes there's these little arrows on the side of the screen to imply that you can go that way. So if I kind of want to add those. I'm getting distracted. I'm getting distracted because this serialization problem is really tricky, and I'm feeling stuck all of a sudden, and my mind jumps to something else. I want to focus on this. Oh, wow. Well, whoever watched for like 2 seconds, thanks, I guess. Anyway, I was hoping that somebody would have some interesting ideas in the chat. I keep hoping that someone will fix my problems for me. Man, I just can't think of what to do. Well, okay, here's something we can do. We can just accept the fact that our serialization, although it makes it possible to encode things that aren't immediately visible using the map, we just accept the fact that oh, what time is it? Oh man, I gotta go soon. Wait. No, I have to go in a half hour. Yeah, I have to go in a half hour. Anyway, we can just accept the fact that we're trading the space efficiency of the serialization and the simplicity. Well, is it that simple? Because inferring the layout from a map of tiles is not that clean. certainly a lot cleaner to just read it. I mean, you know, this traversal of the trees is certainly not simple, but, you know, anyway, maybe what we'll do is we'll just keep an instance count as the user is editing, and when they hit the max instance count, we'll tell them you're out of instances. I mean, there was always going to be a limit. Originally, I liked the idea that the limit was just implied by the fact that the map was there, right? Like, whatever you can draw on the map would be saved. But now, because our representation is a little bit less efficient, nets don't cost any more than they used to, but components do, because well, because they do. I don't think there's a way for me to make it any better. The upshot, though, is that unless the user has completely filled the map, which, I mean, why would they be doing that unless they were like a QA tester trying to break my code, right? Unless you completely filled the map, you would never know that you hit the max instance count. And like, how could you draw a real circuit and fill every single square of the map? I mean, I guess you could if you were really clever. I guess you could. The other problem, by the way, with this idea, I'm not using this idea at all because there's too many problems with it. Like this case here that I've drawn on the right means that actually we still need some way of knowing whether it's a junction or a gate. Actually, well, we can solve that problem by adding the junctions to the list of elements, like the array of elements at the end. So maybe that's not an issue, but like what if I just have a gate sitting out in space, not connected to any nets? You know? Like that just doesn't work with this idea. So we're kind of back to the move to plus 1 byte for the type. Okay, a move to command is 2 bytes, right? I mean, what if I change, okay. An element is a type, we'll give it 6 bits and the relative x 2 bits. I think that works. And having 64 different component types I think is pretty decent. And, you know, we could even do a type 7 bits, relative x 1 bit. Dx is this value plus 1. So if I have a bunch of like densely packed squares, then everything is just 1 byte, 1 byte, 1 byte. And if I have a checkerboard pattern where it's like, you know, it's like square, empty, square, empty, square, empty, then it's still 1 byte each for all of these because the relative x is either 1 or 2. And then if I have square blank blank square, whoops, square blank blank square blank blank square. Then this is 1 byte for the tile, 1 byte for the move to, 1 byte for the tile, 1 byte for the move to. So that's okay. Now that we have given ourselves 7 bits, can we encode the connected nets? No, I don't think so. We're already using 5 bits at a minimum for the element type, and then we would need 4 bits at a minimum for which of the ports are connected. What if, what if we encoded the connection information in the net tree as opposed to in the gate? What could that look like? Well, I've already said how it looks like. I mean, we wouldn't do this trick because, like, so the idea of this trick is we wouldn't need to keep the coordinates for the gates. We could just keep them as a list of elements after the list of nets, and then automatically place them on top of all the squares where we have multiple nodes banging into them. The reason that doesn't work is because a gate could be connected to just one thing or to nothing, in which case this trick wouldn't work. So that just doesn't even work in the first place. But, you know, let's say we do actually add in the extra coordinate in the net. And then when we place a gate, you know, let's say we were reading the array of gates, and now this time every gate comes with an implied coordinate, right? Either by being immediately preceded by a move to command, or by being part of like a chain of back-to-back gates after a move to command. So every gate we place, we know what coordinate it ends up at. So let's say it ends up here. Okay, great. Well, we know that there's a net there connected from the bottom, so we connect it to that port on the gate. Problem is, this makes gates, so with the move to and all of that, gates have an amortized cost of 1 byte each, in the worst case. But if we now if we now say that to connect a gate to a net, you need to add that coordinate to the net. Now they have, in the worst case, an amortized cost of 1 byte for their coordinate information, plus their type information, plus 4 bytes for the up to 4 nets that can point into it. So every component has an amortized cost of 5 bytes. In the worst case. I mean, the normal case would be much better, right? Like, are you really connecting every single port of a gate every single time? Do you really have your nets and gates so densely packed as to fill every available square on the grid? Like, you know, in the average case, you would never hit an amortized cost of 5 bytes per gate. was hoping someone had ideas for me. Okay, wait a minute. The worst case that we can imagine for this serialization scheme, is something like this, which I'm not going to think about what it means, but you basically have a checkerboard of gates. This would be the worst case, and wires between them. Now, if you did this, then you are getting essentially, now let's think about it for a second. This net would have, well, let's imagine this extends infinitely in all directions. So for this net here, you have its root, which has an amortized cost of 1 byte because it's in the list of move to commands and component types. A net is a component type. Well, I shouldn't say component type, but like a net is an element, right? So the root is an amortized cost of 1 byte, and then we have essentially 4 children. So child, parent, child, parent, child, parent, child, parent. So that's 5 bytes for this net object. 1 byte for the gate, 5 bytes for the net, 1 byte for the gate. But this is an unsolvable problem. Like, I don't think I can do better than that. That's not true. I can do better. Because if with each gate I keep 4 bits to say which of its neighbors are connected, then I actually just need 1 byte for this net. Is that true? Can I get away with just 1 byte? Well, we'll think about that in a second. Like we might need to have a special case for like a single dot for a net because like it has no children. So I guess it would just be like a single parent, and the rule is when we go past the root, but that parent costs 4 bits. But each of these gates is now 1 byte plus 4 bits. And each of these nets, let's pretend it's 1 byte, even though it's probably 1 byte and 4 bits. So we actually can do better. We actually can do better. Man, I gotta go soon, and I'm no closer to dealing with this than I was when I started. I don't even think I've written a single line of code. I've just been thinking about how to do this. Let me just explain something real quick. This is totally tangential. Don't misunderstand me. I'm not expecting these streams that I'm doing to be popular or anything. I'm not really recording them for anyone but myself, like my future self, to go and refer to things. Or like if somebody asks a question, I can dig it up in the streams and say, okay, here's where I did it. But it's not like, I never really imagined or intended that this would be something you would just sit down and watch while eating popcorn or something. So that's why I don't really care about like long extended periods of time where the screen is totally static and I'm just rambling about something, because you know, it's not like I was hired to work on a TV show and I'm putting out bad TV. Like, I'm just doing my thing here. Okay, tangent over. So I think I like the idea of serializing it, honestly, because it's just, I think, easier than saving it to the grid. And I mean, saving it to the grid is dead simple, much simpler than serializing, but deserializing from the grid is quite complicated. It's really complicated. I mean, is it though? Because we basically just have a lookup table between tile numbers and what it is. And for every tile number, like, we know what its connections are. Okay, well, there's another option here which I've known I could do and I just haven't thought about, but the other option is just make the map smaller and reserve some space for metadata. And the metadata, it's like, well, you can only have so much of it, right? Like, I forced labels to be 10 characters or smaller, and you can only place, I don't know, 100 labels or something. And for the wave viewer, you can only see up to 8 things at a time, say. And then the wave viewer doesn't even save history. It just shows you whatever it recorded after you placed the probes. There is something else, though, that I just realized. Because I'm only using half of the sprites, I actually have a free bit that I can use. Oh, man. No. Well, okay, this is crazy, but... Okay, but... What if, okay, what if we, for every grid, every square in the grid, we use that extra bit from every single square of the grid to squeeze out more space? We can do that. Actually, I kind of like that. I kind of like that a lot. Is that really what I'm going to do? Is that really what I'm going to do? The map is 128 by 64. Divide that by 8 to get a number of bytes. 128 by 8 is 1024. And I have all the sprite flags to work with. I think this can work. I think this can work. So the graphics flags is 256 bytes, that makes sense. I can squeeze out 1024 bytes from the map. So that gives me 1.2 kilobytes to work with. I mean, that is more than enough for me to have a bunch of labels. Okay, I'm sold. I'm sold. I'm sold. Serialization, sorry pal, but it was never meant to be. Although, you know, I did do a lot of interesting thinking here, so we will put this in the ancient category. Rejected serialization ideas. Yeah, so actually all we really need is deserialization from the map. So, I mean, this is insanity, right? It's insanity, but we can use the sprite flags, which I currently have no use for, and the extra bit of every square of the grid to save metadata. Okay, so let's work on, so serialization is pretty much done already, okay? In the sense that, this is actually something else I've been thinking about. Maybe we'll do that now so that I'll write at least one line of code before I have to leave in 10 minutes. So you see over here where's draw grid? Oh no, this is the wrong tab. Right here. Instead of OX, OY in full, we can instead do width and height. Oh, but this actually draws it to the real map. Oh, that's fine though. Of course that's fine, yeah. To do. And actually, let's not to do it, let's do it. OX, OY. Local W equals W or 16, local H equals H or 16, W and H let you override the width and height of the drawn area. Default is 16 by 16. So now everything should work exactly the same. I'm sure this is the same. Man, it would be really good if I could have some kind of regression test. Don't ask me how to do that though in here. I mean, yeah, I think this is fine. Yeah, I think it's fine. So for serializing, so let's go down here into helper functions. I mean, this is dead simple. Function serialize. Right? It's like, don't think twice about this, right? It is draw grid 0, 0, 128, 64, C store. So let's actually put this in a tab for save load. And let's just call it save. Save. I mean, we're going to add more stuff here, but save, I don't know, circuit, or save design. Draw grid and C store. I mean, that's all there is to it. From base RAM to cart ROM. So we want to put this at 0x1000 from our 0x1000 with length 0x2000. I mean, that's it. That's the whole thing. How many cycles does this take? It probably takes a lot of cycles. Well, I mean, it probably takes a number of cycles dependent on this number. Where's the address map? I keep losing that. Yeah, so 0x1000 for 0x2000. And now, how far can I get in load design here? I can't, I mean, I have to go soon. I mean, I don't have to go soon, but the place I need to go to opens at 9:30, and I see no reason to drag my feet. Which is, I mean, I just finished saying that, but I am dragging my feet. I'm not even dressed yet. I've been working on this since I woke up pretty much. But load design, step 1. Place all gates and junctions. So we will actually scan through it. So the first thing we do is C load, or what's the opposite of C store? Reload. Step 1, place all gates and junctions. This incurs a full 128 by 64 traversal. Step 2, second pass through, I guess I'll call this a pass. Second pass through the tile map to connect nets. I mean, it's not efficient. We could obviously make it more efficient, but this is going to be a lot simpler to write. And we don't care if this takes time, not in the slightest. You know, saving and loading happens at the whim of the user, and users, like, if it takes a few seconds to save and load, users don't care. Or, well, I'm gonna tell them not to care because, like, you know, I mean, come on. I mean, I could, so to do it all in one pass would just be like uselessly difficult, right? So we're gonna need something here, which is we need like a lookup table. Need lookup table mapping tile number to something we can use in the code. I mean, that's it though, right? Because as we scan through on the first pass, the rules are simple. The first pass is, if it's a net, ignore it, move on with your life. If it is a component or a junction, then just create an object for it. Bada bing, bada boom, done, right? Then you go through the nets. For every, it's simple, right? For each tile number, if net, ignore, else make new comp or junction object and put it in global table. I guess the first thing to do would be to empty out all the global tables in the grid and all that. Clear global tables. Clear grid. Oh, wait a minute. I can do that in a much simpler way. Hooray for GC. Okay. And for each tile number, do if net ignore, otherwise make a new component or junction object and put it in global table. This is pretty simple, right? Because essentially what we will do is just map every tile number to the fields that we need for a component, right? Because those fields are, for gates it's negators, for ridges it's delay length, for junctions it's type, and then we have the tile offset and the lookup value base for the components. So, you know, these are all, I mean, we could just put prototypical objects in our lookup table, and then deep copy them. So that we can make a helper function for deep copy. You know, okay, hold on. I have a, I don't think you'll be able to see it, and you shouldn't either, but I have a to-do list of things I need to do today. Let me see, because I've already started coding, I'm really getting into it, and, you know, what's my timeline like? I need to do that. I need to pack, and then how early do I need to leave if my flight is at, so maybe I'll leave here at "3 hours prior to departure." Good God, they just want me to just sit there and twiddle my thumbs. Hold on, I am bargaining to see if I can keep working on this right now. 1 second. I just need to check the times and all that. Well, I think 3 hours early is a little bit excessive.
let me ask my buddies. Okay, you know what? I don't need to do this while streaming. I can just start the stream again later. What am I even doing right now?